Welcome. This video is going to start looking at the properties of acids and bases. Acids get their name from a Latin word meaning sour, and for a long time chemists have known that acidic things taste sour, change the color of litmus from blue to red, and corrode metals. Bases, or alkalis on the other hand, get their name from an Arabic word for ash, and for a long time chemists have known bases feel slippery, change litmus from red to blue, and can remove fats and oils from clothing. We also know that acids and bases are key players in air and water pollution, in global warming and its effect on the chemistry of the oceans, and also in the action of drugs in the body. The other thing we know now is that lots of acid-base theory revolves around equilibrium. So back in 1777, this French scientist proposed that oxygen was the universal acidifying principle. He said acids were any compound containing oxygen and a nonmetal. And he actually was pretty close because many acids are hydrogen with an oxyanion. But there's also hydrogen with just a single nonmetal like HCl. And in fact, hydrochloric acid is the one that they first realized was only hydrogen and chlorine with no oxygen in it. So once this was discovered, they needed a broader definition. And a Swedish fellow, Arrhenius, came up with this definition that still works well. Lots of acids and bases, particularly any that are aqueous, which is most of them. So his definition says acids dissociate or ionize, which is just a fancy word for fall apart. They fall into the positive and negative ions that make them up. So they dissociate in water to form the hydrogen ion, the H+, and then the negative anion attached to it. Bases, on the other hand, dissociate in water to form hydroxide, the OH-, and the cation, or the metal that goes with it. So when acids and bases combine, the hydrogen and the hydroxide ions get together to form water, HOH, and the cations and anions form a salt, or an ionic compound. And this process is known as neutralization. By the way, just an interesting side point, when Arrhenius made his proposal as part of his doctoral work, he was given the lowest possible degree, but he was later awarded a Nobel Prize for his work because he realized back in 1887 that the rapid increase in CO2 from industrialization, all the coal burning plants and stuff, was likely to affect Earth's temperature. And now here we are, almost 150 years later, still debating whether or not that's actually true. His definition, by the way, still covers 99% of the acids and bases we'll be studying. So again, to sum up, an acid is a hydrogen plus a nonmetal or polyatomic ion, and a base is a metal plus a hydroxide. So you can easily look at a formula and know if you have an acid or base. The hydrogen will be at the front end, usually, and the hydroxide will typically be at the back end. So what about the ones that aren't quite covered, that other 1%? Well, those are the ones where water isn't involved, or when you're dealing with an insoluble solid, something that won't dissolve in water. And then the way those are covered, two fellows, Bronsted, the Danish guy, and Lowry, the British guy, published the same idea in 1923. So they both get credit. It's called the Bronsted-Lowry theory. And they both focused on the transfer of hydrogen ions, or the H+ ion, during an acid-base reaction. And acids are defined as the H+ donors, and bases are the H+ acceptors. Since the acid is an H+ or proton donor, and the base is the proton acceptor, that means the acid has to have a hydrogen it can give up. So this is just like Arrhenius. And now the base must have a lone pair of electrons to donate or to be able to bond with that hydrogen ion. So this also means the acid is often left with a negative charge, while the base often picks up a positive charge. So a couple examples. HF can ionize in water to donate an H+ and leave behind an F-. So HF is considered an acid in this model, both the Bronsted-Lowry and the Arrhenius model. NH3 can accept that H+ and become NH4+. So NH3 is considered a base in the Bronsted-Lowry model, even though there's no OH- with it. The other thing with the Bronsted-Lowry theory is this idea of conjugate acid-base pairs. And the best example I can think of is if you think about in foreign language where you conjugate verbs, you change the tense, you conjugate, think of as changing or transferring. So here's the idea. An acid can't donate an H+ unless there's a base available to receive it. Just like in ionic bonds, somebody can't donate electrons unless somebody else is there to accept it. So when this happens, the reverse reaction also becomes a possibility. So in my first reaction here, my forward reaction, I have HA, my acid, so hydrogen with some anion group. I've got my base, and then on the other side, the A minus has donated the acid. So you see the H is gone over here, and it is moved over to the B. So the acid is left with a negative charge, just like we predicted. The HB has picked up a positive charge and taken that hydrogen ion. But now what if we look at the reverse reaction, because it became a possibility? In the reverse reaction, where I've rewritten it as a forward reaction, HB now would be the one donating the hydrogen. So up here, the H was donated. Now the H is being donated back to HA, and B is being left without the hydrogen. So now down here, this is really, HB plus is acting as my acid, A minus is acting as my base. So you can see the roles have just been reversed. The acid has become a base, the base has become an acid. So we call these conjugate acids and conjugate bases. So A minus here would be my conjugate base. My acid becomes a base. My base would become my conjugate acid. And when I run the reverse reaction, I have an acid and base dissociating back into another acid and base. So these are our conjugate acid-base pairs. HA and A minus are an acid and base. B and H plus are a base and an acid. And I will have some examples of those in a couple of slides to give you some practice on it. Another thing to talk about with conjugate acid-base pairs is H2O and H3O plus is a conjugate acid-base pair found in all aqueous acid-base solutions, because anytime you have H plus dissociating in an aqueous solution, some of that H plus is going to become hydrated, or it's going to join with the H2O, because H2O, remember, has two lone pairs. So it can pick up, it can be a hydrogen acceptor, and that would make it H3O plus. So anytime a proton released from an acid ends up hydrated or combining with H2O, you will have some H3O positive ions in there. And so we could talk about them also being conjugate acids and bases. Big thing here is that H3O and H plus are used pretty much interchangeably, because H plus is really just, or H3O plus is really just an H plus that's become hydrated or is attached to a water molecule. So it gets many names. It's called hydroxonium, oxonium, or hydronium ion. I tend to refer to it as the hydronium or hydrogen ion. So here's that practice for the conjugate acid-base pairs. This one says write the conjugate base for each of the following. So that means I want to go from an acid to a base. And remember, the acid loses an H plus to leave behind a base. So that means I should remove an H plus, because these are currently acids and they're going to give up an H plus to form a conjugate base. So this first one, if I take an H plus off, that would leave behind NO2 minus. H3O, if I lose a hydrogen ion, would leave behind H2O, and the H plus takes that positive sign with us, so it'd just be neutral H2O. NH4 would be similar, and H plus would leave behind NH3 with no charge. H2PO4 minus has already lost one hydrogen, because phosphoric acid is usually H3PO4. So if it loses another, it would become HPO4 2 minus. And this brings up the point that when you have an acid like phosphoric acid, which is H3PO4, it loses the hydrogens one at a time. It's a single ionization. Only one hydrogen gets peeled off at a time. So this would be a likely scenario that it could go from H2PO4 minus to HPO4 2 minus. H2CO3 could give up that first hydrogen and leave behind HCO3 minus, and HF would leave behind just F minus. So those would be the conjugate bases. On the next slide, we're going to do just the opposite, write the conjugate acid. So now I'm going to go from the base to the acid, and remember, a base becoming an acid has gained an H plus. So I simply add an H plus to each of these. So this would become HCN. The H plus cancels out the Cn minus. The charges cancel out. The PO4 with the 3 minus gains just one hydrogen back at a time, just like it only loses one at a time. So this would become HPO4 2 minus. H2O would become H3O plus. OH minus would become HOH, or we more commonly call it H2O. You could think of it either way. CO3 would pick up just one hydrogen at a time and become HCO3 minus. And NH3 would become NH4 plus. Now you might recognize some of these from the previous slide where NH4 lost the hydrogen to become NH3. So this is the base, this is the acid. The difference is whether it's gaining or losing that hydrogen. Water also, it can lose a hydrogen to become OH minus, can gain a hydrogen to become H3O plus. That brings us to this idea of amphiprotic. Protic just gets its word from proton, okay? So amphiprotic, like amphibian, can go on land or water. Amphiprotic means it can lose or gain the proton. Acids are the proton donors, bases are the proton acceptors. Amphiprotic substances like water can either gain or lose that proton. For example, if I have HF in water, it can become H3O plus and F minus. In this case, H2O is acting as a base. But if I have NH3 and I put it in water, it's going to tend to become NH4 plus, and now the water has acted as an acid. So up here it's a base when combining with an acid. Down here it's an acid when combining with the base. That's amphiprotic. The other big category of amphiprotic substances are polyprotic acids. Once they've lost a hydrogen, for example, carbonic acid, H2CO3, when it loses that first hydrogen and becomes HCO3 minus, it could either gain a hydrogen and go back to H2CO3, or it could lose the other hydrogen and become CO3 2 minus. It all depends on the conditions. But that's the idea of amphiprotic.